All right. At this point, we're going to start looking at transient problems where the time derivative is important. And we're going to start that by looking at what we call lumped capacitance methods. So in transient problems, we can no longer, of course, assume steady state. So the time derivative is no longer 0. So now we want to think about how we can simplify the problem. The time derivative here represents the energy stored or released during temperature changes. And this is actually a pretty common transient problem where you have one object moved from one environment to another. Think of putting a pizza in your oven. You move it from the freezer to the oven, so that changes the boundary condition. And now the pizza is going to heat up. So we're going to assume that thermal conductivity is basically infinite. If that's the case, we don't have to worry about temperature changes within an object. The temperature is assumed uniform everywhere. So when we do this, we have to ask, when can we make this assumption? And we can make this assumption when the conduction resistance is much less than the convection resistance. Now, conduction resistance, right, is length over Ka, and convection resistance is 1 over Ha. So we can convert this using those definitions, and we can define that HL over K is much less than 1 for the lumped capacitance model to be valid. And when we do that, we call this the BO number. HL over K is defined as the BO number. And instead of much less than 1, which is kind of a vague description, we use the quantity BO number has to be less than 0.1. When we're doing this analysis, we have this length scale. This length scale is going to be determined by the geometry. It's going to be the volume of the system divided by its surface area. That's always what it's going to be. So whenever you're in doubt, just take the volume of the object, you divide by its surface area, and that gives you the length scale you need here. So this gives us the characteristic length, and it basically represents the average distance heat has to travel in order to escape the object. This definition makes it pretty easy to find the BO number for relatively complex geometries. Now we can note that for a plane wall, this length scale is just the length, the distance between the two sides of the wall. For a cylinder, it's just radius over 2, and for a sphere, it becomes radius over 3. Now, the next question we have to ask is, how reasonable is this? I mean, if we consider Fourier's law, right? If the temperature is uniform, then the temperature gradients are 0, and there is not going to be any conduction. So it's really not physically accurate. However, it's pretty reasonable if we think of lumped capacitance as a way of finding the average temperature in the material, and then making the assumption that the surface temperature is very close to the average when we find the convection heat transfer from the surface. And like I said, this is a pretty reasonable approximation when the convection resistance is much bigger than the conduction resistance. But it's not exact. This is an engineering approximation that allows us to get a close enough solution that we can make decisions about design problems. So we talked about not having temperature gradients. So if we don't have any temperature gradients, then we can't use the heat equation. So instead of using the heat equation, what are we going to use? And the answer to that is we're going to go back to the first law of thermodynamics. So this is the same version we used earlier, except in this case I've converted U into CT, and our convection term here is using the total energy. So we're going to make some assumptions. We're going to neglect heat generation completely. We're going to say the object is not generating heat. We're also going to neglect work. We're not going to worry about work. And we have a solid object, so we don't have to worry about flow. So this is going to simplify the equation because now we only have heat transfer through the surface and energy storage terms. So that allows us to simplify the equation a little bit. Now if we assume that the temperature everywhere is the same in the object, then we can apply convection heat transfer for the heat flux. And we can use heat flux equals H times T surface minus fluid temperature. So that gives us this version of the equation. Now we're going to simplify this equation a little bit because right now it looks kind of complex. We're going to define the excess temperature as theta, as T minus T infinity. We can also define it And then so what we end up with is HA times theta is rho C volume, which is the amount of heat that this thing can absorb per unit temperature change, times d theta dt. And this is a much easier problem to solve, and it should, just by looking at it, you should be able to recognize that this should have an exponential solution because d theta dt depends on theta. So from here, this is an ordinary differential equation. We talked about the solution should look exponential. So the final solution here is going to be that theta over theta initial is an exponential function of t and this time constant tau. And tau is the multiplication of the thermal resistance times the thermal capacitance. Here your thermal resistance is 1 over convection coefficient times surface area, and your capacitance is density, volume, and specific heat. So here, this represents the resistance to heat moving out of the object, and this represents the capacity or capacitance of the material to absorb heat. So in this way, the lumped capacitance model behaves much like a thermal circuit, or an RC circuit in electrical circuit analysis. Now, this is a pretty simple and convenient method. We can reasonably readily extend it to cases with heat generation, and we'll talk about that on our next slide. But we can also look at this time constant and see how it behaves. If we go to dimensional analysis, we can look at this t over tau, and we can substitute our definitions for RC, and we get this HA time over rho VC. So we can actually break this up into two different terms. One is HL over K, and one is alpha T over L squared, where alpha is K over rho CP. We already recognize this, right? This is the Biot number, which we looked at when we were determining whether the lumped capacitance method was valid. This is the Fourier number, and it represents a dimensionless time. It's a new dimensionless number for us. It represents the ratio between the conduction of heat and the storage of heat. So when we do that, we can see that t over time, or t over tau, is just Biot number times Fourier number. So we can actually graph the solution to this equation as theta over theta I as a function of Biot number times Fourier number, and we can converge every single lumped capacitance problem to this one single line. So this line describes every single lumped capacitance problem as long as the Biot number and the Fourier number are correctly defined, which is a very interesting feature of the solution, and it's very useful in engineering analysis. So the next question becomes, what happens if we have heat generation? In nuclear engineering, this is important because we have radioactive decay, which produces heat. So in many nuclear applications, we're going to have some heat generation. We start back at the first law, and if we apply our simplifications, we end up with this equation right here. So you have the heat generation term, you have the heat loss term, and the heat storage term. So energy storage is going to be equal to the difference between production and loss, which is a pretty standard engineering balance. Now this is a nonlinear, inhomogeneous, ordinary differential equation. So we have some difficulties here. Now we're going to simplify it a little. We're going to again define the excess temperature as T minus T infinity, and we're going to define these two parameters, A and B. A is HA over rho VC, which we've already seen, and B is Q dot V over rho VC, which scales the energy generation to the energy storage. And this is going to change our equation a little bit, and it's going to give us the d theta dt plus A theta minus B is equal to 0. The next step in this is to produce an additional simplification. It gives us theta prime is theta minus B over A. Now B over A is a constant. So if you look at d theta dt and d theta prime dt, they're the same. So when we do that, we can substitute, and now we have d theta prime dt and plus A theta prime is 0. This we can solve. This is exponential. So we get this exponential solution to this. And then if we substitute theta minus B over A back into this equation, we end up with this result. So if we have heat generation and convection only, then our lumped capacitance can be described by this equation here. And you'll note that this A is the same time constant as we saw in the regular lumped capacitance with no heat generation, but we've modified it by these additional terms. And in fact, at steady state, after a very long time, we can see that this exponential term is going to go to 0. So at very long time, if this term is 0, this is going to be the final temperature after a very long time for our lumped capacitance problem.